Since the earliest days of firefighting, the primary goal in the fire suppression process has been to supply water for extinguishment, and water is usually conveyed to the fire through hose lines. Fire hose has been around since the 17th century. While hose has evolved to some extent, it still does essentially the same thing. Water flows through it from point A to point B. However, the technology of firefighting has advanced tremendously since this old pumper rolled the streets. In the old days, for example, an effective interior fire attack was virtually impossible because firefighters had insufficient personal protection equipment. Also, the nozzles of yesteryear were limited, to say the least. In fact, you were lucky if you had a nozzle that you could control on and off. Today, departments are utilizing much more sophisticated apparatus, but hose lines nevertheless remain the backbone of the fire suppression effort. Fire hose itself has advanced considerably through improved design. More significantly, other firefighting techniques have matured, furthering the advancement of firefighting technology. Today's nozzle, combination nozzle, better equips the modern firefighter to battle the blaze. And with the development of self-contained breathing apparatus and other improved personal protection gear, firefighters are able to launch a much more aggressive fire attack while safeguarding against personal injury. The presentation you're about to see analyzes an effective fire attack, a single hose line advance to the kind of house fire that we all frequently experience.
The first step in the fire suppression process is the establishment of a water supply. When a hydrant is used, one firefighter will be designated as the hydrant man and make the necessary connection. Using the department's accepted hand signals, he motions the driver to proceed. The hydrant man opens the valve to test the hydrant's flow, ensuring that the hydrant is operational.
Engine 8 on location. We have a 3-story dwelling with smoke showing from the 2nd story.
10th floor, Engine 8.
Okay, give me an 1 3/4 line. Is there anyone else in there, man? Okay, don't worry, we'll take care of this. I'm going in to check out the 2nd floor.
The company officer enters the building to evaluate fire conditions, but only after telling another firefighter. The attack team will be following shortly. Observing the light interior smoke conditions, he waits to don his SCBA. Simultaneously, hose line preparations are taking place. The firefighter designated as the nozzleman takes the nozzle and slips his arm through the top 2 folds of hose and walks quickly toward the fire. The nozzleman should not attempt to drag the entire hose length behind him, but wait for his backup hoseman to provide slack. The hoseman places the remaining hose on the ground. He immediately begins unraveling the hose to straighten out any kinks, as well as providing slack for the nozzleman. Meanwhile, the firefighter from the rear step is breaking and connecting the supply line. The officer begins his search of the 2nd floor, surveying each room for smoke and victims. He scans the hallway to determine the path that the hose line will need to take. Once at the door of the fire room, he kneels and quickly sizes up the conditions in the room. He closes the door completely and plans the attack on the fire. Downstairs, the nozzleman enters while the hoseman gives him plenty of slack to advance hose line up the stairway. Meanwhile, the hydrant man and the driver have been coordinating the charging of the supply line. Once the pump connection has been made, the 2nd hoseman relieves the 1st hoseman and stays near the door to guide the hose line through. The advancing firefighters avoid bunching up behind the nozzleman. Instead, they attempt to stay evenly separated. This enables a more balanced weight distribution, resulting in a faster and safer advance. With the supply line charged, the hydrant man is free to back up the attack team by assisting the hoseman at the top of the stairs. As they advance the hose up the stairway, they direct it toward the outside wall, anticipating its expansion. At the top of the stairs, the nozzleman continues down the hallway toward the officer. The hoseman follows and moves all of the excess hose line into a side room. He makes certain that there is a sufficient amount of hose to reach the farthest point in the fire room. The hose line is now advanced to the hallway outside the fire room. With everyone in position, the officer calls for water.
Engine 8 command to Engine 8. Start the line.
Engine 8, 10-4. The nozzleman bleeds the air in the line and checks that the nozzle is operational. Once all the air is out, he shuts down. The attack team must now don full protective gear. Each firefighter must put on his SCBA mask, put on his helmet with the ear flaps down, and replace his gloves. Also, the nozzleman should never enter the fire room alone. A backup should always assist and be available if something goes wrong. At this point, the coordination between the ventilation and attack teams is critical. Without ventilation, the attack would be ineffective, as well as dangerous. After the line is supplied with water, the windows in the fire room are vented from the outside. The medium fog pattern with a nozzle stream selector. When everything is ready, the officer opens the door, and the team enters, crouched down to avoid the heated fire gases. The nozzleman opens the nozzle and cools the upper portion of the room by directing the nozzle in a vertical clockwise manner. Then, switching to a straight stream, he sweeps the floor, burning the wood. The nozzleman then selects a medium fog pattern again to continue battling the blaze. The nozzleman continues to advance, keeping one leg extended to test the floor in front of him. By using only enough water to knock down the flames, the thermal balance stays intact. This maximizes the ventilation effect. A second engine company has arrived to back up the first. Their primary responsibility is to advance a second hose line to protect and support the first attack line. A second line would be started only after water has been supplied to the primary lines. Effective communication is critical in coordinating the company's activities.
All right, on second line on floor above the fire.
The backup company uses hose from the first company's engine. The second engine stays close to the hydrant to provide pumping support. With the fire knocked down, the attack team must stay in control of the room. The backup firefighter checks the room for signs of reignition. The area near the doorway, having just received a rush of fresh air, is potentially dangerous. After all excess glass is cleared out of the window, the nozzleman begins water stream ventilation. From 3 to 4 feet away, he directs a fog pad, slightly smaller than the dimensions of the window, through the window. This rapidly dispels smoke and heat from the room. The nozzle should now be adjusted to create the greatest air velocity. Once the first hose team is in control of the fire room, it becomes the second hose team's responsibility to extinguish any extension on the floor above. The two teams should always be aware of each other's position in case protection or support is needed. It is important that the initial attack line be in operation before lines are stretched and charged to the floor above. This protects the second attack team from becoming trapped above the fire. The second team has their area under control. Other available personnel assist with opening potential fire passages. Although much smoke is cleared, firefighters must continue to use their SCBAs because dangerous gases still fill the house. Several key points should be considered as the operation moves into the overhaul stage. First, water damage must be kept at a minimum. For example, when faced with a smoldering mattress, sofa, or chair, The nozzleman uses a straight stream in a back-and-forth pattern just inches away. This is effective in both extinguishment and limitation of water damage. After the initial attack is under control, a firefighter who isn't busy should inspect and tighten any leaky couplings with a spanner wrench. The nozzleman must shut the nozzle down slowly to avoid a water hammer. A sudden stop in the water flow could burst a hose line. Possibly the most important aspect of engine company operations is the care and preparation of the hose line. This equipment is vital to the operation and must be ready for the next fire. The hose should be carefully inspected as it is packed back into the hose bed. Each department has its own standards for loading hose into hose beds, but every loading pattern should be designed for efficient hose line advancement the next time it is needed. This operation has been only one example of an effective fire attack. Another engine company may have elected to battle this blaze differently, yet still produce the same successful results. Furthermore, other conditions or factors may have dictated a variation in this company's strategies. For these reasons, a few variations on advancing hose lines need to be examined. Ideally, hose lines are advanced dry and uncharged. However, certain circumstances demand the advancement of charged lines. For example, it is often necessary to charge the line prior to entering the burning structure. In addition to its obvious extra bulk and awkwardness, the advancing of charged lines demands increased communications between the nozzleman and his backup. Otherwise, the backup may force his nozzleman out of control. Many fire departments are taking advantage of the superiority of inch and three-quarter hose lines. However, many departments still often utilize larger diameter hose lines, such as 2.5-inch lines. These larger lines are usually used in exterior fire attacks and require some special considerations. More firefighters are required to put the heavier line in service. The higher flow rates increase the nozzle reaction, necessitating 3 firefighters to stabilize the line. The 2 backup firefighters must anchor the line so that the nozzleman is able to launch an effective attack. It is sometimes necessary for engine company personnel to advance charged line up the ladder to attack a fire. The procedure begins by raising the ladder so that the tip is resting about 3 feet above the window. Each firefighter, positioned about 10 feet apart, takes a leg lock to keep both hands free. The charged line is pushed upward from one firefighter to the next. The nozzleman directs the nozzle through the ladder and properly secures it with a hose strap. Once anchored, the nozzle can be opened. A successful initial fire attack requires a great deal of coordination from a great number of people. By being familiar with the proper procedures and techniques, every firefighter will be better prepared to participate in a hose line advance. Here is a brief review of the operation. Upon arrival, establish an adequate water supply. Next, begin an immediate size-up of the fire conditions from both the exterior and interior of the burning structure. Begin the initial hose line advance, being careful to fully unravel the hose to prevent kinking. Advance the nozzle to the fire room, but be certain there is sufficient hose amassed on the fire floor to advance to the seat of the fire. Charge the attack line and bleed all the air out of the line prior to making the attack. Be certain that the attack team is ready and protected by safety gear, and that the fire room is properly ventilated. Then make the attack. Cool the heated fire gases in the upper portion of the room, and then attack the fire itself. Once the fire is knocked down, the attack team must stay in control of the room, checking for any reignition. Fog-streamed ventilation is used to evacuate the smoke and heated gases from the building. Also, all possible exposures must be checked for fire extension. Lastly, the hose must be carefully inspected and the hose bed repacked to ensure that the next fire attack can be just as effective. The procedures examined in this presentation represent just a few of the many practices that can be employed to effectively advance a hose line. Each firefighter must follow the standard operating procedures adopted by that firefighter's department. With all engine company personnel working together, a safe and effective hose line advance is ensured.
Time is a firefighter's worst enemy at a structural fire. You must quickly attack and control the fire to minimize danger to life and property. The fastest method of controlling a structural fire is applying effective fire screens. In this program, we'll demonstrate how to size up fire conditions, estimate necessary fire flow, outline attack strategy, and select and apply various types of fire streams. To select a successful attack strategy, you must first size up fire conditions by identifying the seat of the fire, phase of burning, fuel load, and avenues of fire spread. The seat of the fire is the origin of intense heat generation from which the fire draws energy to grow and spread. Locating a fire seat is not always easy. Sometimes it may be hidden from view. Your initial attack strategy should consider the most probable seat of the fire, but should be flexible enough to change if the fire seat is not where you estimate it to be. The phase of burning will directly affect your strategy. For a fire in the incipient phase, use a quick attack, applying a fire stream directly to the fire seat. Attack a fire in the pre-burning phase by first reducing its temperature, then approaching it and applying fire streams to its seat. Attack a fire in the smoldering phase by first venting off heat, smoke, and gases, then attack using tactics similar to those used on a free-burning fire. Fuel load is the amount of combustible material that could become involved in the fire. To size up the fuel load, you must estimate the quantity, volatility, and potentially hazardous nature of the fuel involved. The quantity of fuel is the amount of burnable material that may become involved in the fire. The contents of a structure contribute fuel to the fire. A storage warehouse packed with flammable goods represents an extremely high fire load, while a machine shop containing non-combustible metal machines and parts may contribute little to the fire load. The structure itself may also contribute fuel to the fire. Combustible construction materials and lack of fire-resistant features can aid fire growth and spread. Fire-resistant construction, which includes non-flammable construction materials, fire-retardant interior finishes, and fire-stopped concealed spaces, may inhibit fire growth and spread. Also consider the potentially hazardous nature of the fuel. Flammable liquids and gases, explosives, and some toxic chemicals are hazardous fuels. When you encounter hazardous substances, take safety precautions to protect occupants and firefighters before you attempt to stabilize the incident. Fire spread is the fourth size-up factor. A fire may spread through open spaces or barriers by radiation, convection, conduction, and direct flame contact. Wherever you identify a possible avenue of fire spread, try to place a fire stream between the fire and the unburned area. Fire flow is the amount of water necessary for fire stream application. Supplying adequate fire flow includes estimating how much water is needed and selecting resources to deliver the flow. The amount of water needed is the water necessary to extinguish the fire. Water extinguishes primarily by lowering the fire temperature and also by displacing oxygen. Water lowers the fire temperature by heat absorption and conversion. Absorption occurs as heat is transferred from the fire to the water. When a pound of water absorbs 1 BTU of heat from the fire, the water temperature increases by 1 degree Fahrenheit. For example, if a pound of water at 50 degrees is applied to a fire as it approaches its boiling point, 212 degrees Fahrenheit, it will absorb 212 minus 50, or 162 BTUs from the fire before turning into steam. The second way that water lowers fire temperature is by conversion. Conversion occurs as water turns to steam. A pound of water absorbs about 970 BTUs of the fire's heat as the water is converted to steam. Therefore, 1 pound of 50-degree water absorbs 162 BTUs as it's heated to 212 degrees, plus 970 BTUs as it converts to steam, for a total of 1,132 BTUs. A gallon of water weighs 8.3 pounds. 8.3 pounds times 1,132 BTUs per pound equals about 9,390 BTUs per gallon. Therefore, 100 gallons per minute can potentially absorb about 939,000 BTUs per minute. Water also extinguishes fire by displacing oxygen. As water turns to steam, its volume expands nearly 1,700 times, creating a large cloud that pushes oxygen and flammable vapors away from the burning fuel. A fire stream pattern affects the rate of heat absorption. Water fog absorbs heat much faster than a solid stream, because the fog, which consists of fine water droplets, exposes more heat-absorbing surface to the fire than an equal amount of water in a solid stream. It's possible to calculate necessary fire flow based on heat absorption and fire stream pattern, but the task is too difficult and time-consuming to be practical at the fire ground. So several rules of thumb have been developed for quickly estimating the required fire flow. You can determine the maximum fire flow needed in gallons per minute by dividing the total number of cubic feet in the involved structure by 100. For example, a fully involved one-story structure is about 40 by 50 feet. The necessary fire flow equals the cubic feet 40 times 50 times 10, height of one story, divided by 100. The answer is about 200 gallons per minute. Delivering adequate fire flow where it's needed requires careful selection of resources, including water sources, hose lines, and nozzles. Choose a source that will supply your estimated fire flow requirement. The type and number of attack lines depends on the type and size of the fire. For incipient fires, you may use 1.5-inch line. A short burst should knock the fire down. For residential fires that are beyond the incipient stage, you may need several lines, at least 1.5 inches in diameter, to attack the fire and protect exposures. If there are floors above the fire floor, you may need to lay lines above the fire floor to keep the fire from extending upward. For large industrial and commercial structures, attack lines should be at least 2.5 inches in diameter, discharging 200 to 250 gallons per minute. Each line should cover about 1,000 square feet of space. Master streams should be supplied by 2.5-inch or 3-inch hose, preferably Siamese, to decrease friction loss. Whenever possible, use a backup crew with a charged line to ensure a safe escape for the attack crew. The final consideration for applying adequate fire flow is the type of nozzle. Choose a nozzle for each line that discharges the desired fire flow in an effective pattern. There are 4 main types of adjustable stream bog nozzles. You must maintain recommended nozzle pressure, usually 100 psi, to produce effective pattern, reach, and flow. The 4 types differ in their treatment of discharge. Non-constant gallonage nozzles discharge less water and increase nozzle pressure as you decrease the pattern angle, provided that pump pressure remains constant. So when you decrease the angle during an attack, you apply less water to the fire. Constant gallonage nozzles maintain a constant discharge rate as you change patterns if pump and nozzle pressures are not changed. So during an attack, you can change from a wide to a narrow or straight stream without affecting your discharge. Adjustable gallonage nozzles also maintain a constant discharge rate as you change patterns if pump and nozzle pressures remain constant. In addition, you can select your discharge rate from a range of settings on the nozzle. However, if you increase the discharge setting during an attack, pump pressure must also be increased to maintain constant nozzle pressure needed to produce a good fire stream. Automatic nozzles likewise maintain a constant discharge rate as you change patterns and can supply a range of discharge rates. But unlike other nozzles, as pump pressure increases, this nozzle automatically increases its discharge rate. In addition, nozzle pressure remains constant as pump pressure increases, which ensures your stream always has good shape and reach. For solid stream nozzles, the discharge capacity depends on 2 factors: nozzle pressure and diameter. The nozzle pressure affects the velocity of the water, that is, how fast it's flowing out of the nozzle. Increasing the nozzle pressure will discharge water at a faster rate. The diameter of the nozzle also affects discharge. At a given nozzle pressure, larger diameter nozzles discharge more water than smaller nozzles. To apply a large amount of water, such as 350 gallons per minute or more, Master stream nozzles are most effective. Master streams may discharge as much as 750 to 1,000 gallons per minute. Based on your size up, you may choose one of two major attack strategies, offensive or defensive. An offensive attack is designed to aggressively assault and extinguish the fire. A defensive attack is designed to confine the fire to its initial location and prevent it from intensifying or spreading to exposures. Regardless of your strategy, you should observe two tactical rules. Always work from unburned property and direct fire streams on the three main points of fire stream application. Working from unburned property is extremely important. If you work from burned property, your fire streams may push the fire into uninvolved areas, causing more damage and possibly endangering occupants. But if you work from unburned property, you push the fire back upon already burned fuel. 3 points of fire stream application are exposures, avenues of spread, and the seat of the fire. Exposures are structures and property that could be damaged or consumed by the fire, including portions of the fire structure, and structures or property not attached to the fire building. Avenues of spread are other application points. By applying water to avenues of spread, you may stop fire growth and spread. The final application point is the fire's seat. As soon as possible, initiate an immediate and concentrated attack on the fire's seat to reduce heat and extinguish the fire. The actual tactics used to apply fire streams vary for fog streams, solid streams, master streams, and special fire streams. The fog stream has become the firefighter's main weapon for fire suppression because of its tremendous heat-absorbing ability. The major characteristics of fog streams are the size of the water particles and the space the stream occupies. Fog streams are made of many small water particles which greatly increase the surface area of the stream, allowing it to absorb heat faster than an equal amount of water with less surface area. Fog nozzles create smaller water particles by breaking up the solid core of water from the hose as it passes through the nozzle. In a periphery deflecting fog nozzle, the core of water strikes a deflecting stem in the center of the nozzle, which breaks the water into small particles that are deflected against the outside of the nozzle outlet. An impinging stream fog nozzle divides the core of water into several small streams, which are impinged or broken against each other. Many fog nozzles use a toothed wheel that spins when the nozzle is opened, chopping the water into even finer particles as it's discharged. The second characteristic of a fog stream is the space that it occupies, determined by the pattern, wide, narrow, or straight. A wide-angle fog occupies more space and therefore can absorb heat very quickly. However, a wide-angle fog has a very short reach, so it may not be effective if you're trying to extinguish a fire in a large area. A narrower angle fog has a greater reach than a wide angle, but its heat-absorbing capacity is lower. A straight stream covers very little area, but has much greater reach. Straight streams are used to reach far into a fire area, or to apply a concentrated stream of water on a specific hotspot. Advancing a fog nozzle inside a structure is difficult and dangerous. Always wear protective clothing and SCBA, and never enter a burning structure alone. Before entering, bleed entrapped air out of the hose and nozzle. Don't stand in front of a door that opens into the fire area. Crouch low to one side, remove your glove, and feel for heat with the back of your hand. If you feel there's a great danger of backdraft, you may need to ventilate the structure first. Otherwise, open the door slowly, staying low and to the side. When the door is opened, smoke and heat will vent over your head. Advance with a wide-angle fog pattern pointed toward the ceiling to reduce heat and protect yourself. Work the nozzle in a circular pattern to absorb as much heat as possible. When you've gained entry, decrease the angle of the fog stream and work it well over the ceiling of the room. If you're hitting the fire, you'll see smoke, then smoke and condensed steam, and finally a cloud of condensed steam. As soon as the fire is knocked down, shut off the nozzle. Applying too much water can upset the thermal balance, disrupting the smothering effect of the steam blanket, or producing too much steam, which could engulf and burn you. Apply a second burst of water fog if the atmosphere remains hot or the fire flashes back. As hot spots flash back, extinguish them with short bursts using a straight stream pattern directed at the seat of the fire. If advancing a fog nozzle through a heavily smoke-filled area, feel ahead for obstructions, open spaces, or stairs. If you can't see the fire, slowly open the nozzle in a narrow fog pattern and work it in a large, sweeping arc across the ceiling. If the heat does not dissipate, apply more water and redirect your stream. When you're advancing a fog nozzle on a burning exterior, advance slow using a wide-angle pattern applied in a circular motion to protect yourself from radiant heat. When you're close to the fire, reduce the angle of the stream, still working it in a circular motion to absorb heat. 2 or more fog streams may be used to advance on a large exterior fire. When advancing multiple lines, interlock the fog patterns to create a wall of water fog. The nozzle operator or commander should call cadence or give audible advanced signals. Use a backup line to cover the nozzle crew's retreat in case a hose bursts or a brisk wind blows away the water fog. Solid streams offer better reach and penetration than fog streams and can be used to project fire streams over great distances. 3 factors determine the effective reach of a solid stream: velocity, volume, and angle of application. The velocity of the stream is its speed or rate of forward motion. The faster the water travels as it leaves the nozzle, the farther it will travel before gravity pulls it back to Earth. Increasing nozzle pressure will increase stream velocity. Volume is the rate of discharge leaving the nozzle, usually measured in gallons per minute. High discharge streams will reach farther than low discharge streams at the same nozzle pressure because of the water's momentum. The angle of application can be adjusted to compensate for the effects of gravity to project a solid stream the desired distance before gravity pulls it back to Earth. High angles of application will give the stream great vertical reach, but it will not reach very far forward because the velocity is vertical. Very low angles of application will allow the stream to be pulled down before it reaches the objective. A 32-degree angle will give the stream maximum horizontal reach. When you apply a solid stream, make sure it reaches the objective before or at the point of breakover. The point of breakover is the point at which the stream breaks into showers of spray. Although the stream may travel far past the point of breakover, it's lost much of its forward momentum, and wind or convection currents could divert the water's path before it reaches the fire. Master streams are used to apply a large volume of water to a fire. Master streams are primarily used defensively on large fires to keep them from spreading. Before using a master stream, make sure it's been correctly placed and is used appropriately to achieve your strategic objectives. Improper use of a master stream can inhibit ventilation, cause serious water damage, and spread fire to uninvolved areas. In addition to the standard fog and solid stream nozzles, there's a number of special purpose nozzles used by fire departments. Broken or impinging stream nozzles are used to disperse a coarse spray of water into an involved space that cannot be entered. This rotary broken stream nozzle is placed into an involved cellar after a hole is cut in the floor. When opened, the nozzle disperses a widely diffused rain of water droplets throughout the area. The piercing nozzle is another special nozzle designed for attacking fires in a concealed or inaccessible space. Piercing nozzles are characterized by a hardened tip, which can be forced or driven through a wood, metal, or masonry wall. Once inside, the nozzle disperses a fine spray in the involved area. Water additives are also special fire streams which include firefighting foams and wetting agents. Firefighting foams are generally used to extinguish fires that cannot be extinguished by water alone, such as those involving flammable liquids. Water alone sinks below hydrocarbon fuels, such as gasoline, and mixes with polar solvent fuels, such as alcohol and ketone. But foams float on top of these fuels and stop combustion. Foam extinguishes fire in 4 ways. It smothers by creating a barrier between the fuel and the oxygen. It suppresses the emission of flammable vapors. It separates flame from the fuel source. And it cools many fuels below their ignition temperatures. There are many types of foam, including protein-based foams, alcohol foams, synthetic surfactants, aqueous film-forming foams, and high-expansion foams. Foam is made by combining foam concentrate additives with water in the proper proportion, then agitating the mixture. Low-expansion foam nozzles use venturis to draw in small amounts of air, which agitate the stream, producing foam. High-expansion foam nozzles use mechanical blowers to agitate the foam solution with a large volume of air, creating a thick foam blanket. Wetting agents are water additives that increase the penetrating ability of water. Wetting agents break down the surface tension of water, allowing it to penetrate Class A fuels and cool them rather than bounce or run off. Synthetic surfactants and AFFF function as wetting agents when applied in a solid stream. Foam streams and wetting agents require special application techniques. In general, apply foams as gently as possible to create a thick, airtight blanket over the fuel. Take care not to agitate the fuel surface or strike it directly. If possible, bank a foam stream off a nearby object to decrease its forward velocity so it falls gently on the surface of the fuel. If there's no suitable banking surface, apply the foam in a high arc so it falls gently on the burning surface. When fighting a flammable liquid spill, aim the foam stream at the ground just in front of the burning surface so that the foam deflects off the ground and rolls on to the fuel. The rate and time of foam application varies with the type of foam, severity of the incident, and weather conditions. Plan to use enough foam to blanket the area at least twice so you can reapply the foam blanket if necessary during cleanup. When you've fully covered the fuel surface, stop applying the foam and take precautions to avoid disturbing the foam blanket. Any type of agitation breaks down the foam and decreases its effectiveness. Some foams, such as AFFF, heal themselves if the blanket is disrupted, but avoid agitating the foam. Foam should not be applied to fuels that are gaseous at normal temperatures. Once the fuel warms up and becomes gas, the gas will escape through the foam blanket. Foams cannot be applied on pressurized leaks of flammable liquids or gases because the pressurized fuel will push the foam away. And since foams are mostly water, they must not be used on energized electrical equipment or materials that react with water, such as magnesium or sodium. Proper fire stream selection and application is essential to quick and effective fire suppression. To select the most appropriate fire stream for your task, you must size up fire conditions, estimate and supply the necessary fire flow, choose an attack strategy, and select the proper equipment and tactics to accomplish your strategy. Your ability to correctly select and apply fire streams will help you to gain control of fires quickly and efficiently.